Hello everyone, welcome back. In this video, we're going to talk about the various functions that we will encounter throughout our course. Now, these functions are typically used as models to help us understand real-world phenomena and to make predictions about the future. So the first function we'll define are polynomials, and polynomials are functions that take on this form. We have a of n times x to the n plus a of n minus 1 times x to the n minus 1, all the way down to a2 times x to the power of 2 plus a1x plus a naught. Now n is any non-negative integer, and the numbers a naught through a n are constants, which are called the coefficients of the polynomial. Now the domain of any polynomial is the set of real numbers. Now if the leading coefficient, a of n, is not equal to 0, then the degree of the polynomial is n. So in other words, if we have a non-zero coefficient, a of n, then the degree of the polynomial is going to be the highest power of x in the function. Now a polynomial of degree 1 is of the form p of x is mx plus b, and it is called a linear function. So the highest power of x that appears in the polynomial is 1. A polynomial of degree 2 takes on the form ax squared plus bx plus c, and this is called a quadratic function. So the highest degree, or the highest power of x, is equal to 2. Now a polynomial of degree 3 is of the form ax cubed plus bx squared plus cx plus d, and this is called a cubic function. So the highest power of x that appears is 3. So let's have a look at the graphs of these various functions. So on the left we have the equation y is equal to x, and the graph of these linear functions are straight lines. Now in the second figure we have the function y is equal to x squared over 2 minus 4, so these are quadratic functions, and the graphs of these quadratic functions are called parabolas. And on the right we have the graph of the cubic function y is equal to x cubed over 16. So it will start in the third quadrant and then end in the first quadrant, and other cubic functions may start in the second quadrant and then end in the fourth quadrant. So next we can define a power function which takes on the form f of x equals x to the power of a, where a is a constant and x is our independent variable. So for this function, there are several different cases that we will consider. Now in the first case, if a is equal to n, where n is a positive integer, then these are polynomials with only one term. So these are examples that we've looked at earlier, but only dealing with a single term. Now in the second case, if a is equal to 1 over n, where n is a positive integer, then the function will take on this form, x to the power of 1 over n, and this can be written equivalently to the nth root of x, and these are called a root function. So for the root function, we'll consider a few separate cases. For n equal to 2, then what we have is the square root function. So we have the square root of x, and the domain is from 0 to infinity, including 0. Now the graph of the function is going to be the upper half of the parabola x is equal to y squared. Now for other even values of n, the graph of the nth root of x will be similar to the square root function. So the fourth root or the sixth root of x will have graphs that will be very similar to the square root of x. Now for n equals to 3, then we have the cubed root function. So the cubed root of x, and the domain of the function is all real numbers. And if we have the graph of the nth root of x, where n is an odd number, then the graphs will be very similar to the cubed root of x. So the fifth root and the seventh root of x will be similar to the cubed root of x. So here is the graph of the square root function. So it's only defined from 0 to infinity. And on the right, we have the cubed root function, which is defined for all real numbers. So we have one more case for the power functions. And if a is equal to -1, then what we have is x to the power of -1, which can be rewritten as 1 over x, and this is called the reciprocal function. Now the graph of the reciprocal function is called a hyperbola, and the coordinate axes are asymptotes of the function. So here is the graph of the hyperbola, y is equal to 1 over x. So both the x-axis and the y-axis are asymptotes of this function. Next, we can define a rational function, and the rational function takes on the form p of x over q of x, where both p and q are polynomials. So it's the ratio of two polynomials. Now the domain of the function will consist of all values of x such that q of x is not equal to 0. So this function is defined as long as the denominator is not equal to 0. So here we have the graph of the rational function. We have x to the 4 minus x squared plus 1 all over 8x squared minus 32. So we see that the function has vertical asymptotes at -2 and +2. So let's have a look at finding the domain of this function so that we can verify that it has these two undefined points. So our function is x to the 4 minus x squared plus 1 all over 8x squared minus 32. So to find the domain of the function, we need to look for when the function is undefined. So the function is undefined when the denominator is equal to 0. So the denominator of this function is 8x squared minus 32. So if we solve the equation where the denominator is equal to 0, then we can find the points for which the function is undefined. So here we are able to solve for x. So if we move the 32 to the right-hand side, we have 8x squared is equal to 32. And then if we divide by 8, we get that x squared is equal to 4. So now if we want to solve for x, we will take the square root of both sides. And whenever we take the square roots of an equation, we need to remember to include plus or minus. So we have the square root of x squared is equal to plus or minus the square root of 4. So we have that x is equal to plus or minus the root of 4, and the root of 4 is equal to 2. So the function is undefined when x is equal plus or minus 2, and so the domain of the function is going to be all values of x such that x is not equal to plus or minus 2. So in interval notation, we can write this as the interval from -infinity to -2 union -2 to +2 union 2 to infinity. So it is the set of all real numbers excluding plus and minus 2. So we have a few more definitions. So a function f is called an algebraic function if it can be constructed using algebraic operations. These operations include addition, subtraction, multiplication, division, and taking roots, starting with polynomials. So all of the functions that we have defined so far are examples of algebraic functions, since these are functions which are constructed by using certain algebraic operations using polynomials. Now, a function that is not constructed by using a finite combination of algebraic operations are called transcendental functions. And the examples of transcendental functions that we'll come across are trigonometric functions, exponential, and logarithmic functions.